So hello everyone, in this part we will talk about the FSK demodulation and modulation in Simulink. So first of all you have to create a blank model. Okay, so if you remember from the theory that first of all we need a data stream, and then we have to add that data stream with the carrier's signal. So to generate the data stream, we have to go to the browser and search for Bernoulli binary generator that will generate some pattern, data pattern. So be here. So here, this one, you have to add this one here, and to change the setting, probability of 0 will be half, it's okay, and source of initial speed will be from the parameters, and initial seed you can give any data, so depending on your value it will give some data pattern. So let's give some 55, sample time will be 0.1, so in 1 second we will get some data beats. Okay, the samples per frame is 1, is okay. Okay, so you have to just click OK. So now the next part is the carrier signal. So for carrier we can use some sine wave. You can go to sine wave. You can pick anyone, and for this function, so it will be time based, and the time will be from the simulation time, not external. So amplitude is 1, is okay. So frequency is in radian per second, so you have to add 2 pi for 1, that means high signal, we will use 1600 megahertz, and sample time will be 1 by 1000. Okay, so for the 0 we will just, I duplicate this one, so we will use half of that. It's okay. So now click OK. So this will be our carrier function. Next, to check the transmitted data, you can use some kind of scope over here. So go to library, you can search for scope. Here it's this scope. Okay, so this you can write it here. This is for carrier for high 1, and this one is carrier for 0. Okay, now as we see in the theory part that we have to invert the this data, the 0 carrier, we have to make it 1 for that. So we have to calculate, we have to do some tricks over here. So how we can invert this data? So let's see, so if you have a data stream of 1 0 1 1 0 1 1, and this is 440. Then if we subtract 1 from this, then we will have the inverted data, and if you do the absolute value of that data, then we will get 0 1 0 0 1 0 0 1. So we will have some inverted data of this one. So let's use that one here. So first of all, you need to go to the library manager again. You can search for sum. So you have sum over here. Then as we will minus a constant, we need a block of constant. So you can choose this one. We need the mathematical function of absolute. So for that, a b is here is our this function, and for the modulation we need the product block. So you can, yes, and you can just Control C and Control V for to duplicate that one. Okay, so we have all the equipment for the modulation, and again, if you remember the thing, we have to add the both signal to this one. So we need another of these things. So Control C, you can use Control V for paste. Sorry, you need this one over here again. Okay, so let's connect all the things together. So first of all, so from here one signal will go to our this product format, and another will come over here, and this constants will go from here to here, and this is actually this will this one will subtract from this one. So you have to double click this one, make it plus minus. Okay, now the data will get the positive data, and then it will go to our product term. Okay, so from here actually we will add these two signals. This will be added over here. Okay, and this will be actually our output, and this one also we need to add this thing. And to see the transmitted data, we will use some scope over here. So now we want to see the transmitted data in the each of the steps we did over here. So first of all, we use this one, so we can write it like transmitted data. So transmitted, so you can use it tx data, over here, tx data. Okay, so then this is the uh, show block name, so it will then appear. This is our carrier signal for 1, carrier signal for 2. This is actually modulation part, so you can write it, show the block name. This is another modulation, and this is the add. Now we can use another scope. Actually from here also you can see, if you want to see the data, if you want to see the carrier data, so you can name it carrier signal. And we can make it 2 input, as we have 2 different inputs. So go to signals and ports, number of inputs, make it 2. So one will come from here and another will come from here. So this is actually our carrier signal. And another one we will look after the modulation, so over here. So let's see. So in this scope actually we will see the modulated data. So you can okay, and then we will have another scope to see the combined data. So this will be actually our main modulated output. So for this case actually we need just one port. This is the modulated signal. Okay, and for simulation time you can use 1 second, 2 second to see the output, and let's save it. Okay, now if you want to see the output and everything, so you have to run the simulation first. So just click the run button for the simulation. So it's already done, and let's see the transmitted data first. So you can see this is our transmitted data. So this is uh, for first 2 seconds. So we have 0 1 0 0 1 0 1 0 0 1. Okay, so this is our transmitted data, and next let's see the carrier signals. So now we have actually two signal in one graph, so you can change the layout. Okay, so both are very high, but if you change see for a very small time, like for okay, so if you want to see for a little time being. So this is for 1 and this is for actually 0, so it has high frequency and this one has low frequency. So this is actually our carrier signal, and if we do the modulation for with each with the data with the message signal, then let's see how it looked like. So again we have actually two signal over here. So you see, if you do the multiplication or product, so wherever we are getting 1, we are getting high frequency over there, and wherever we are getting 0, we are getting low frequency. So let's check again. You see, this is very high frequency and this is very low frequency. So now just what we have to do, we have to add these two signals, and that is what we are doing over here, and after that we will get that signal. So if you want to see that signal, so just double click this one, and now if you zoom it, you will see that the both signal are now added. So this is actually the modulation part, and if you want to see the spectrum how it looks like in the A50 version, you have to add the spectrum analyzer with to that. So how we can add the spectrum analyzer? So we have to go to browser again and search for spectrum. Sir. So you can choose anyone. So where we want to see the data, so let's check first of all the carrier. So this is the for carrier, and to see the data again you have to go to the you have to run the simulation again. but before that you have to do some of the settings. So go to the settings. We want to we don't want to see the power, we want to see actually the amplitude. So for that we have to change from power type to RMS type, and we want to see the both sided spectrum. So you have to go to the trace option and you have to select this one. If it is not selected, two-sided spectrum, you have to select this one. Okay, now if you do the run the simulation, it's taking us a little bit time. You see, for this one, for this carrier, the frequency was actually our 1600 megahertz. So you see that in positive side 1600 megahertz, and in negative side we have some spike. So this is okay. And next one, uh, we need to check after the adding of this thing. So let's copy this one and paste it over here. Okay, and then again you have to run the simulation. So this is for this one, and also you need to see this one, so it will come. The simulation is taking a little bit time. So this is for this one. Okay, now we are getting spike at two frequencies. One was at 800 megahertz. If you zoom it, so you can see that one is at 800 megahertz and another one is at 1600. So you see we are getting spike at 800 megahertz and 1600 megahertz as we are sending the message signal in these two frequencies. So this is actually the modulation part. Now we will do the demodulation. So for that, actually what we need, first we have to add some noise. So to add some noise, we will go to library again and search for the channel noise AWGN. So you see this is actually white Gaussian noise. We'll add this one over here. Okay, and to check the signal, how the signal changes, you have to add again. You can add these two things again. After the channel, so you can check how the signal looks like with this. And for the parameter settings, you can check anything, and for here you have to use various variants. From mask. Okay, so this is done. Okay, now if you run the simulation again, let's see how our signal looks like after adding the noises. So these two signals are before adding noise. We can cross this one. So this is before noise actually data, and this is after noise. We'll zoom it, and this is spectrum is after the noise. Can cross it right now. So now if we zoom it, we can see the difference. This is before noise. Let's check for fast 0.2 second, and this is after noise. You see the difference? So this is very clear signal, but this is very distorted. You see the condition of signals became very rough, and from the spectrum, like the A50 transform, you can see also here actually there is no noises, but in this case we have very noise in the signals, but still the data has very high value with respect to noise. Okay, now the next part is to do the demodulation part. For demodulation part, if you remember from our previous theory, what he did, we need to add some detector. So this detector actually also act as a modulator, so we have to multiply this signal with our carrier signal for the same frequency and everything. So let's do it again over here. So we need again two product term. You can just Control C and Control V, use Control C and Control V for, and we use the same carrier. For carrier 0, this one. So as we just copy and paste over here, so all the features will be also copied here, so it will become same. So you see this is twice by 800 and sample time is this one, and for this one is twice by 600 megahertz, yeah, sorry, hertz. So if you want to see again how it looks like after the modulation, you can use another scope over here. So here you have to use 2 port. So this is just for how the signal looks like, and it is very important. If you can see the changes, you can understand it very clearly. And then actually let's check first how it looks like. You see, again we are having two signal over here. So previously actually this was actually our signal, and what we did actually, we add some carrier with these things, and then our this is our actually the signal. And if you zoom it, you can see that like for 0.1 second this is actually close to 0, so this is in the lower term, this is in the higher term actually, as our data bit was 0 1, so this is 1, and for this case this is little bit in higher term, so this is 1, and this is uh, in the lower side, so this is actually 0. So if you use some filter, then we can make reduce some uh, unwanted noises and unwanted signals. So now what we have to do, we have to design some filter, and to do that let's go to library again, and here you have to search for filter. There are actually lots of filters. We'll use some digital filter, so digital. So filter designer, you can use this one. So this is our filter, and we need two filter. One is for zero signal and one is for high signal. You have to connect this thing. Okay, now in the design parameter you have to give some parameters for the filter, so how it will look like. So first of all, it obviously we have to reduce the low frequency. So how can we check that one? So to do that, let's use some spectrum analyzer again here to see the condition of our signal. And let's run the simulation again. Okay, so we need 3 and 4. So you see, so now we have to collect these, we have to filter out all other data, and we have to just need this data. And for designing the filter, we have to check the condition. Okay, and this is for actually 3, this is for the upper one, carrier 1, and this is for the carrier 0. Okay, so we have this data now. Now we can go to design the filter. You can see that till 0.05, that means it's 50 hertz, we have some data. And here it may be, if you zoom it more, so we have to pass this whole data. So our frequency that will pass, we need to from -20 to +20, so we can use 20. And for highest stop, we can stop near about 50. Okay, so let's go for our filter designer again. So it will be a low pass filter and a fire method, and here it will be like our frequency base. So this sampling frequency should be same as our sampling frequency, which was 5000. And this is actually P pass and P stop. P pass actually that's we decided about 20, and P stop will be 50 hertz. So how we get that value? So if you see the spectrum, so you see that till the 10 hertz frequency we have some data, and we have some also low data in the till the 50 hertz frequency. That's why we are selecting. And it this frequency, pass frequency and stop frequency, totally dependent on your design, how you design it. So uh, if you increase the stop frequency, you will see some unwanted data will be in your system. Okay, so now let's design this one. You see, this is actually your filter design. So you will get the data and all other will be neglected. And we have to do the same thing for this one too. Okay, so this one is also the same actually. Okay, and this is okay. Magnitude and specification you can make it same as this one. So now our filter is designed. Now again we can see the filtered signal. So just you can copy and paste this one, and let's check these two data. So after filtered, what happened? You have to run the simulation again. Actually, this is a very big simulation. You have lots of spectrum analyzer, that's why it's taking much time. To reduce this, you can decrease the simulation time to 1. Okay, so this is before filter, and this is after filter. Okay, we are getting some value. So Okay, so from here actually you can see also this one. So this is transmitted data, then we need the before filtered data. This is the filtered data, and this is before filter. Now you can see some good values of the signal, right? You have here, you can see this is 0, so this is 0 0.2 till 0.2, this is 0. If you zoom it a little bit, okay, till 0.1 we have high value here, so you see we are getting higher value over here, and 0.2 we are getting lower value. So now what we have to do, we have to add these two signals first. So let's, or you can do it from here, or you can just copy this one. And in this case actually we will actually subtract this signal from this signal, so you have to use minus, then we will get the actual signal. So you can use another scope over here. To see the output data. Okay, to run the simulator little bit faster, you can comment out this thing. We don't want to see right now. Okay, so this is actually after adding actually both signal, this will be our final signal. Let's run it again. So you see we are getting this kind of some values, and if you see our transmitted data, this is, so you will see some pattern that first of all we are getting 0, so you see this is below 0, and then we are getting high, and then the 0, so this is 0, and then we are getting high, then again 0, then again high, 0, high, 0, high, high. If we go to here, then 0, 0, high. So we already almost got the signal, but we have to make it looks like this one. So we have to make it like digital pulse signals. To do that, we can use some comparator, right? So if you see, if the signal is below 0, we can say that this is 0, and if the signal is greater than 0, then we will use 1. So we need a Boolean type comparator. Okay, so to find that, we can go to library manager again, and you can find compare constant. Okay, compare to constant, so you can use this one. And also there is a fixed compare to 0, so as we will compare to 0, so we'll click this one, and you have to select this thing, and this is less than, we have to actually find the greater or equal to 0, and this is a Boolean type. Okay, so now if you see the signal, that will be our actually demodulated signal. Control C, Control V. This is actually our demodulated signal. Okay, if you now run the simulation, you will see the changes right now. So our scene data, and if you double click this one, you will see the receipt data. Okay, so you can see initially it is 0, so there is some delay, and you can actually reduce this delay depending on your filter design. So first of all, we are getting 0, then 1, then 0, then 1, 0, 1, 0, 1, 1, 1, 1, then again 1, and then 1. So what we send from our transmitter, actually in the receiver end, actually we are getting the same value with some of this delay factor, but it will not don't create any problem. And if you design the filter designer perfectly, you can reduce the delay also. So let's check with 10. Filter design done, and this one for okay. So let's run the simulation again. And this is our TX data. This is our demodulated signal. You see, yeah, now the delay is very low. And if you want to see some others like demodulated signal 4, this is okay. Now if you want to see some other signal also, which one can we see? This modulated signal is, so you can see the whole process now. So how we started and how we get the data at a ground station. So if we talk about the example, so from satellite actually we are sending this data, and from that data is the carrier is added with that, if you with the message data for 1 high frequency is added, for 0 low frequency is added, and then when we are sending it from satellite to ground station, in the environment many noise can be added. So this is actually the noise channel, so we added noise over here. Then next task is in the receiver end. When we receive the data, the first uh, task is to demodulate that data. So for that we add a carrier, uh, we multiply the carrier signal with the signal to increase the amplitude, and then we design the filter to remove the unwanted frequency from our signal. And then what we did, we actually added these two signals, and then we compared that signal with respect to 0 to get the actual data. So this is actually a full process, and you can also add spectrum at the different point to see how the frequency response is changing. So that's all from the FSK part. In the next part we will talk about the P escape, that means phase shift keying. So thank you all. So thank you all for your patience. Now you can do the simulation of FSK in Simulink. Right. Now you can do the modulation and demodulation of FSK in the Simulink. Thank you.